I'm Yuanchao. I'm from North Carolina State University. I will introduce our work called Hardware-Based Domain Virtualization for Intra-Process Isolation of Persistent Memory Objects. This work is a collaboration with Huazhen University Science and Technology and the University of Central Florida. In the traditional memory hierarchy, the DRAM will provide fast memory access, but the data in the DRAM is volatile. Disk can keep data persistent, but accessing disk is slow. And now there's a new technique called the persistent memory, which combines the advantages of these two. The processor can just use regular load and store instructions to access persistent memory, and it can keep the persistent data structure rather than the directory in the file system. And the typical program model for persistent memory is called attach and detach program model. The persistent memory is organized as the PMOs, and they are stored in the physical address space. And the attached system calls will memory map the PMO to the process address space by initialize the needed PTEs. Then this process can access this PMO as normal data, and the detached system calls will remove those PTEs, and the process can no longer access this PMO. And the security would be more important for persistent memory. And here is an example. There are two PMOs in the physical address space, and the thread 1 invokes the attached system calls to memory map the PMO1 to the address space, and the thread 2 from the same process also invokes the attached system calls to memory map the PMO2 to the address space. And the thread 2 may use the bugs or vulnerabilities to corrupt the data in the PMO1 to the PMO1 intentionally or accidentally. Then, even after the termination of the process, the corrupted data is still there, and the corruption would be persistent, and it will be propagated to all future usage. So we propose to improve the security by using intra-process isolation. Intra-process isolation will separate the process address space into several parts, and in this example, we separate into two parts, and each part will use to store some data, and when there's an access from one domain to another domain, whatever that is an intentional or accidental access, this access will trigger the error handler, since the permission is not set for between these two domains. And when we set the permission from between these two domains, the interaction between these two domains are allowed, and this boundary can be reset again by unset the permission. And when we apply the intra-process isolation for the persistent memory, we assume we will give each PMO a domain, and it will have a unique domain ID. In the following presentation, we will just regard it as the PMO ID. And the whole persistent memory would be divided into many domains, and there is an efficient implement design to support intra-process isolation from Intel is the memory protection key, and it can provide the 16 protection key. At the runtime, it will map the domains to those P keys. But however, in the typical server applications, it may have many clients that each client could be a thread, and then each client may have its own private data it want to access. So there will have hundreds of active domains need to be mapped to the P keys, but due to the limited protection keys, the frequently remapping for the PK from one domain to another domain would lead to a substantial overhead. And we provide two efficient design to solve this scalability problem. Our contribution is following. We first propose the intra-process isolation to improve the security of persistent memory. And then we first analyze the design of the Mpk to provide virtualization on top of that. And then we provide a more aggressive design called domain virtualization. It it is more suitable for more number of PMOs. And overall, both of our design provide modest area space overhead, and the Mpk virtualization achieve 10 times speed up compared to the software virtualization, and the domain virtualization achieve 50 times speed up compared to the software virtualization. And the following content, including the introduction to the Intel Mpk and the virtualization analyze, and the two designs and its evaluation. First, I will introduce the Intel memory protection keys. In the memory, they may have many pages. The Mpk need to first tag a set of pages with p keys, and then there's a thread private PKRU register that record the permission of those p keys. And when a thread and the thread can use special instructions called write PKRU to set the permission of this thread for a p key. Then, when it want to access one of the pages belongs to this p key, the minimum permission will be checked between page permission and the p key permission will be checked. If the minimal permission is allowed, this access will be succeed. And if another thread want to access the pages belongs to this p key without setting the permission, it will fail to access that. And after the thread 1 finishes its access, it can also use the instructions to close remove this permission. And after that, when thread 1 want to access this p keys pages, it will also encounter the access will also fail to do that. And let's take a look about more detail about the Mpk. To tag the memory pages, all of these pages for one pk need to be tagged. Then, when access to one of these pages, the TLB will load the PTE from the page table. And after that, the PK is used to index the permission in the PKRU register. Actually, the second permission is always the PK1 permission, whatever this PK is assigned to which memory pages or which domains. So when a PMO already occupy a PK and we want to assign this PK to another PMO, we basically need to clean the PK of the original mapping and then set the PK in the PMO2 to finish this remapping. And after that, we also need to store and restore the permission of the PK. It need to first store the PMO1 permission and then put the PMO2 permission in the PK of the PKRU register. And after that, the TLB may still contains out of date information. For example, in here, the page 100 will still assume the PK is the current mapping, but actually it will obtain the PMO2 permission. So the TLB invalidation are needed to remove this out of date information from the TLB. And all of these steps are needed when the program accesses the evicted domains or PMO, and it will have 4,000 cycles, and even though there's a one eviction for 1,000 instruction, it will lead to 400 overhead. And we propose two hardware virtualization design. The first is called Mpk Virtualization, which will remove the first two steps to achieve an efficient virtualization. And then we have a more aggressive virtualization called domain virtualization. It basically further removes the TLB invalidation for remapping. In our Mpk virtualization, when we take a close look of the setting and resetting the PKs in different PMO, we actually find that the PMO actually is a consecutive virtual address. We can just use one entry that contains the virtual address range and the PK to represent the mapping of from a PMO to a PK. Then we just need to modify this entry to finish the remapping. So here is the workflow of our Mpk virtualization design. The memory access to PMO20 it carries the virtual address. When there's a TLB miss, it needs to check both page table and the domain translation table in parallel. Basically, in the domain translation table, it contains the information from the virtual address range to the PK and the permission. And when the evicted PK is selected, here is the PK1, we need to store the permission from the PKRU register of the PK1 to this buffer. And after that, we need to write back the content of the PMO1 into the in-memory domain translation table. After that, the virtual address of the PMO2 access is used to obtain the information of PMO20. Then this information will update the entry to map the PK1 to the domain 20. After that, the permission of the domain 20 will update the PK1 permission. The PK1 will be added to the PT obtained from the page table. The composed entry will be added to the TLB. Then this access will get the PK from the TLB and use the PK to index the permission in the PKRU register. And all the logic of TLB heat doesn't change. So for TLB heat, it keeps the promising features provided by the default Mpk, like there's no extra runtime overhead and there's a fast permission changes. And the design of the domain translation table and its buffer, it removes the system calls requirement for the remapping, and it only need to update the entry 2 times to perform this remapping, and it is fully programmer transparent support. That means the programmer don't need to manipulate the mapping and remapping from the domain to the PKs. Then I will introduce our second design called domain virtualization, which further removes the TLB invalidation for every step, for every remapping. The inefficiency of the TLB invalidation is that first, the index always represents the same PKs, and it doesn't contain the information of the domain. For example, the fifth position will always record the PK5 permission rather than whatever the domain mapping. It may first map to the PMO-X, and when we perform a remap to PMO-Y, actually this information cannot be reflected in the PKRU register, and this information and there would be out of date information in its TLB that map the PMO-X to the PK5, and then the TLB invalidation is needed. Meanwhile, the second reason is that all the threads will hold the same mapping, so the TLB invalidation to all threads are needed. So our idea is to use the buffer to replace the PK mapping. We will directly to control the domain and its permission. The workflow of our domain virtualization is following. For the PMO20 access, it carries the virtual address and it will access the extended TLB. When there is a TLB miss, it will need to check both TLB and both the page table and the domain table to obtain the PT and the domain ID. In the domain table, it basically contains need to translate the virtual address to the domain ID, and then the PT put into the extended TLB will combine the information in the TLB and in the normal PT from the page table and the domain ID from the domain table. Then the access will obtain the domain ID from the TLB, and it is used to check another permission TLB, and it would be backed up with a permission table. In the permission TLB, it contains the information from the domain ID to its permission, and a not found search result will regard this domain as inaccessible, and then the domain permission can be obtained from this permission TLB. And in this way, we actually achieve a real thread private permission control, and there's no TLB invalidation are needed because all the thread will hold its own buffer, and it don't need to synchronize between the different thread, and the permission TLB already contains the information from the domain to the permission rather than the permission itself, so it can perform a fast permission grant, change, or removal. So in our evaluation, we will use two types of benchmark. First is the Whisper benchmark, which builds from the real-world applications for one PMO evaluation. And then we will use the micro benchmark with multi-PMO to perform more aggressive cases evaluation. The access pattern for the multi-PMO, we will just randomly choose a PMO ID to access. And for the architecture overhead, we'll use the sniper simulator to obtain those overhead. For the performance, I will present the micro benchmark result, and the XL means the number of active PMOs, and the YCL is the overhead compared to the no protection program. The ideal virtualization is that we assume there is no overhead of the virtualization. It is unrealistic lower bound of the virtualization, and then the dot line is the software virtualization that can even incur a substantial overhead for just 32 PMOs. And the dashed line is the hardware Mpk virtualization, and it can achieve 10 times speed up for 1000 domain compared to the software method, and it can also achieve 6 times speed up even for 32 PMOs. But due to the TLB invalidation, for 1000 PMOs, its overhead is still substantial. So for our domain virtualization design, it can achieve 50 times speed up compared to the software method for 1000 domain, and for the cross point for 16 entry buffer, the cross point between two designs is about 20 PMOs, and that is because the domain virtualization at a critical path for the TLB hit. There is more result and analyze in the paper. In conclusion, we propose protecting PMO by using intra-process isolation. We uncover the scalability limitation of software Mpk virtualization for PMOs. We designed the hardware Mpk virtualization that builds on top of Mpk, achieving 10 times speed up for 1000 domains, and we designed the domain virtualization that achieve 50 times speed up for 1000 domains. And thank you for your attention. I'm happy to take questions in the virtual conference. Thank you.